I'm Steven.
I'm Russell.
Hey, I'm Cody.
We're Senior Design Group 18.
So our project is a heads-up display for a motorcycle helmet. Why do we want to do that? Simple, safety. If a rider has to take his eyes off the road for more than a second just to look at his dials, he's riding blind. So I mean, if we can have the display right in front of his eyes, he doesn't have to look away, and safety can improve.
As a very high-level overview, our system will consist of a motorcycle and a helmet. The motorcycle will send data to be displayed on the helmet.
Two of the main engineering requirements are to have a wireless communication between the helmet and the motorcycle and a slightly transparent and visible display. The reasoning behind this is because we want the rider to actually see outside of his helmet. Otherwise, our goal of safety goes straight out the window. You know, the reason behind the wireless communication is just like the ease of use for the rider. That way he doesn't have to unplug anything before getting off his motorcycle.
One of the requirements for our system is that the display must show speed, RPM, and the current gear of the motorcycle. Another requirement is that the system must contain no permanent attachments on the helmet or the bike, because we don't want to permanently alter someone else's motorcycle or helmet. The last requirement I'm going to talk about is our system must be economical. That is, we want our system to be competitively priced relative to other products that are currently on market.
So this is the block diagram we chose. The block diagram is kind of split into two sections, the on-bike section and the on-helmet section. To the left is the on-bike section. This includes a power supply, which will power both the sensors as well as a microcontroller on the bike. The sensors will take in different information from the environment or the bike itself, whether that be light, speed, RPM, and just different signals. That sensor and the data will be sent to the microcontroller. The microcontroller will decipher this information through the code and different other calculations that we put into it and send that to the on-helmet microcontroller. The on-helmet microcontroller will be powered by a power supply, and it will also just kind of manipulate that information and be ready to be put onto the EL or thin film transistor display. The display will obviously be transparent and show the different information to the bike, to the rider, so that he can see it without looking down at from his helmet. The display will also be powered by the power supply, but it'll be through the inverter. So the display needs to use high voltage AC signal, and so the inverter will take our low voltage DC signal and create it into that high voltage DC or AC signal to power the display. And that will obviously take the light out to the rider itself. And the other two blocks on here are the motorcycle, where it'll all be put on, and the chassis for the helmet. They'll have all the microcontroller, power supply, and inverter inside.
Within our system, we have two power supply blocks, one on the motorcycle and one on the helmet. The reason we have two separate blocks is because they're physically separate, and you can't have wires going from the motorcycle to the helmet, otherwise we wouldn't meet our wireless requirement. One of the blocks in our system is the sensors block. The reason we decided to put all our sensors into one block is because while they're measuring different information, they're all serving the same purpose as the inputs to our system. I'm going to talk about two of our sensors in particular. That is the tachometer, which detects RPM, and then also the speed, which uses RPM to determine the speed of the bike. For both these sensors, we're going to use what's called a Hall effect sensor. A Hall effect sensor detects magnetic field, and it's basically a digital magnetic switch. So the way it works on a wheel, for example, if you're determining the RPM of the wheel, is you have a magnet on one side of the wheel, the sensor on the other. And to make this example simple, let's say half of the wheel, the inside of the wheel, is open, and the other half is some kind of metal. So every time the Hall effect sensor and the magnet line up with the open part of the wheel, the magnetic field from the magnet can get to the sensor, and that makes it output a low, a digital low. And every time the metal's in between them, the magnetic field from the magnet is blocked and cannot get to the sensor, and it outputs a high, which high is based off the reference voltage that you input into the Hall effect sensor.
So two other sensors we're going to have, other than the tachometer and speedometer, are light sensors. So we have three light sensors, for each have different reasons. First light sensor we have is the ambient light sensor. They'll be on the helmet. They'll be used as a dimming function for the display. So in lighter situations, it'll have a bright display, and in lower or dark situations, we can use less power and have a dimmer display. The other light sensors will be the brake sensor and then the blinker sensors. So these will just detect when the brake or blinkers are on, and it'll signal some type of EL display light on the display inside the helmet, indicating that there's a right blinker or left blinker, or the brakes are being applied. how these sensors are going to work, they use a cadmium sulfide photocell, and they'll be in series with a resistor tuned to a specific point where when the light is shown onto the photocell, it'll lower in resistance, and therefore the signal output will be raised into a certain threshold. And once it goes over that threshold, that light will be turned on the display. So we just need to set the resistor be at the correct value so that it sends out whatever our threshold voltage is at the certain light intensity when those lights are on. And yeah, those are our 3 light sensor systems.
So we have 2 microcontroller blocks in our block diagram, one for the transmitter, which is on the motorcycle, and one for the receiver, which is on the helmet. Now the transmitter microcontroller is going to take data from the sensors. It grabs the voltage from the Hall effect sensor, it grabs the voltage from the light sensors, and then it's going to use some calculations in order to transmit that into the right code. The receiver microcontroller is going to decode the transmitted data and put it into its right variables. All the while, it's going to be turning off segments and turning them on. It's going to continue in this loop, and it's what's called persistence of vision. Persistence of vision is when a light source is on for only a brief amount of time, but to us it looks like it's on continuously. And so that's what our heads-up display is going to be doing. It's going to be turning off on a light, and then it's going to be turning it off right after. And it's going to cycle through all of the segments in order to make it seem like the entire display is on at the same time.
One section of our block diagram is our display. The display is actually the only block in our system that interacts with our rider. So it actually will show the information to the rider and for him to interpret. How we're going to be making our display, we're using an old 7-segment LCD screen, stripping it of all with the plasma and everything else, and then coating it with phosphorus. As we apply a voltage across the LCD screen, the phosphor will actually light up and will make a display. Why we chose this EL display is because it's very transparent when it's turned off. There is some transparency, but it doesn't impede the rider's vision very much. Yet when it's on, it's also very bright and visible, and can be tuned to different brightnesses for different light conditions as well. And this is just really good to help keep the safety as well as the usability of the display to where we need it to be. So the inverter is a different block of our block diagram, and why this is an actual individual block and not a sub-block is because it has a huge impact of actually how our design works. So it has 2 different interfaces, right? So our power supply is going to be 3.3 volts, but the EL display, or thin film transistor display, is going to require a huge amount of voltage, and it's going to be non-DC, so probably in the neighborhood of 1 to 200 VRMS at a frequency of between 300 to 3000. And so we need some type of block to change that over, and that's what our inverter does. Without that block, then you're either substituting that block into either the power supply, which is not supplying power, it's just converting power, or into the display, which has nothing to do with the power. So that's why this is a standalone block. One section of our block diagram is our display. The display is actually the only block in our system that interacts with our rider. So it actually will show the information to the rider and for him to interpret. How we're going to be making our display, we're using an old 7-segment LCD screen, stripping it of all with the plasma and everything else, and then coating it with phosphorus. As we apply a voltage across the LCD screen, the phosphor will actually light up and will make a display. Why we chose this EL display is because it's very transparent when it's turned off. There is some transparency, but it doesn't impede the rider's vision very much. Yet when it's on, it's also very bright and visible, and can be tuned to different brightnesses for different light conditions as well.
So by the end of fall term, we should have all of our designs completed. Winter break, we will be ordering our parts, so that way when we get back, we should be able to start working on them immediately. Hopefully we will have our project done by the end of winter term, and then we can work on additional features spring term. If not, then we will finish up our project spring term.
Well, that was the end of our technical presentation. Hopefully our product will help to improve rider safety.